In our very last video today, we're going to take a look at what are called multiple integrals. This is going to be very similar to partial derivatives that we saw before. With partial derivatives, we treated one variable like a constant, took the derivative, the partial derivative, with respect to the other variable, and we could do multiple partial derivatives, and that's pretty much what we're going to see here, the same exact process with integrals. Our general strategy is we are going to be treating the other variables like constants. One little thing we got to be careful of, though, is before we had a plus c when we took an integral. Now it is going to become plus c of the other variable. In other words, it's going to become a function of the other variable. So if we're taking the integral with respect to x, we might have a lot of y's left over that were the constants that went to 0. And so it's going to be a function of the other variable. And you might see f of x or c of x or g of x or y or whatever the variable is. But it's always going to be plus a function of the other variable. So let's look at a partial integral, if you will. It's just the integral of 3x cubed y squared plus 2xy cubed minus 7 dy. And what's important here is the dy. That dy tells me which variable I'm taking the integral of. It's all of these y's are my variables. Which means the x's we're just going to treat like a constant, and they'll just come out front. So the integral of y squared is y cubed, and then when we divide by 3, we get 1x cubed, plus the integral of y cubed is y to the 4th. 2 divided by 4 is 1/2 x, minus, and then we have a 7y. Don't forget we got to do plus a constant, but that constant is going to be a function in terms of the other variable. In this case, it's in terms of the other variable x. So you might see plus f of x, plus g of x, plus c of x, some type of constant function that only has that other variable in it. I want to notice we could have done the exact same problem, the integral of 3x cubed y squared plus 2xy cubed minus 7. But if we put a dx on the end, that dx on the end changes which variable we are taking the integral of. Now x is our variable, and we're going to treat everything else like a constant. So if x is the variable, we end up with x to the 4th power. Divide the 3 by 4, and we still have the constant y squared. Plus, if x is the variable, we now have y squared. 2 divided by 2 is 1, y cubed, minus the integral of 7 is 7x. And this time when we add our constant function, it's going to be in terms of the other variable, which is y. And while these two solutions might have a lot in common, it's important to note that they are not the same. There are several differences between them, so it does make a big difference which variable we take the integral of at which point in time. Let's try another function. Let's do number 3. For this next example, we're going to do the integral of x times x squared plus y cubed dx. And when I look at this, you might notice this is a substitution type problem. Just as before, we can use all of our integral tricks, substitution, regular antiderivative rules. We can even do integration by parts. All the rules still work the same with multiple variables. So if we make u equal to x squared plus y, That way we end up with u cubed. Du, remember we're taking the derivative with respect to x, is 2x. So we'll multiply by a 2 inside and 1/2 inside. So when we make this substitution, we end up with 1/2 times the integral of the 2x dx, all became, should have been a dx, all became du, and the x squared plus y cubed becomes u cubed. And so we can take that integral, it's u to the 4th divided by 4. 1/2 times a 1/4 is a 1/8 plus a constant, and so all we have to do is replace that u with the constant, with the x squared plus y, I should say. Plus the constant is in terms of the other variable. That constant is y, and we have our derivative. Oops, don't lose the 4th power. That's important. Let's do the same thing we did last time, and that was take the integral with respect to the other variable. Example 4 here. We're going to do the integral of the same function, x times x squared plus y cubed d, and this time we're going to do dy. We did dx last time. So again, dy means the y is my variable. And what's nice here is the substitution is going to really clean up because the x is already a constant, so it can float out as it is. So if we make u equal to the x squared plus y, du, its derivative with respect to y is just 1 dy. So we pull the x outside because it's a constant. We've got u cubed du. And we know that the the integral of u cubed is u to the 4th, and so we take x over 4 plus a constant. And then we just have to replace that u to the 4th with what it equals. And that would be x squared plus y plus a constant with the other variable, which we will call x. Could stop there. I'm just going to clean up by distributing through that numerator. So we have x cubed plus xy over 4 plus the constant in x. And that is our integral with respect to the other variable. And just like with regular integrals, we can do definite integrals as well using this method. We can integrate from 1 to 3 of 6xy squared minus 7y over x plus e to the 4xy. Let's do dx. Since we have done dx, we're interested in x is the variable on each term. The other variables we treat like constants. So x becomes x squared, and we divide by 2, giving us a 3. With the constant y squared still there, minus 7y is a constant, and 1 over x, the integral of that, is the natural log of x, plus e to the stuff is e to the stuff divided by the coefficient of the stuff, which in this case is 4y. And we're going to integrate this from 1 to 3. The difference I'm going to do here is I'm going to say this 1 to 3 is equal to x. The y's are going to stay in this function. So we've got 3 times x, which is 3, squared, y squared, minus 7y natural log of x, which is 3, plus e to the 4x, which is 3, y, all over 4y, minus, and we're going to have to distribute this negative through, making it negative, positive, negative. So we've got 3 times 1 squared y squared plus 7y natural log of 1 minus e to the 4 times 1y over 4 times y. Notice the y's stay in the expression. The x's are replaced with 1 and 3. So when we simplify, 3 squared is 9 times 3 is 27y squared minus 7 times 3 is 21y Whoops, back up. That's not 7 times 3. That's 7y natural log of 3. That 3 is inside the natural log. We can't multiply. Plus e to the 4 times 3 is 12y over 4y. Minus 3 times 1 squared is 3y squared. Plus, what's interesting is the natural log of 1 is 0, so all of that goes away. So we're left with minus e to the 4y over 4y. Combine like terms of the y squareds, we're left with 24y squared. There's a minus 7y natural log of 3. Plus, since these guys both have like denominators, I'm going to make that one fraction e to the 12y minus e to the 4y over the common denominator of 4y. And because this was a definite integral, we do not need the plus c. We have our solution. Notice when it's a definite integral and we put in those limits, the variable we're looking for has disappeared completely. The x has disappeared completely, but the y's are still there. Well, notice the same thing happened when we do the same problem. Integral from 1 to 3 of 6xy squared minus 7y over x plus e to the 4xy, and we take it dy instead of dx. Now you're going to expect all the y's to go away, because we're going to treat the y's like our variable. Everything else is a constant. So the antiderivative of y squared is y cubed divided by 3, leaves behind 2x, minus the antiderivative of y is y squared divided by 2 with the constant, so we have 7 over 2x, plus e to the stuff is e to the stuff, divided by the coefficient, which in this case is 4x, and we're going to integrate from 1 to 3, but these 1 to 3's we need to know are equal to y. 1 and 3 are this time being entered into y, not the x. So we have 2x times y, which is 3 cubed, minus 7y, which is 3 squared, over 2x, plus e to the 4xy, which is 3 over 4x. And then we're going to subtract, so all of our signs are going to switch. We have minus 2x times y, which is 1 cubed, plus 7y, which is 1 squared, over 2x, minus e to the 4xy, which is 1 over 4x. And let's clean up this problem. 3 cubed is 27. 27 times 2 is 54. X minus 3 squared is 9. 9 times 7 is 63 over 2x. Plus e to the 3 times 4 is 12x over 4x. Minus 2x plus 7 over 2x. Minus e to the 4x over 4x. Combining like terms, 54 minus 2 is 52x. The 63 over 2x plus 7 over 2x is going to be minus 56 over 2x, which is nice because that actually is going to reduce to 28. So I'm just going to do that. 28 over x, plus we got a common denominator of 4x, so we'll put those all underneath 4x, and that's going to be e to the 12x minus e to the 4x, and there is our solution. Because we took the integral with respect to y, the y's are gone. We're just left with the x's. So just like partial derivatives, we take the integral, treating the other variable like a constant. But this video was titled Multiple Integrals. These have all been single integrals. So let's actually look at what we came here to talk about. We're going to talk about double integrals, where we work from the inside out. And they're going to work just exactly like you would expect them to. We're going to have an integral from 1 to 2 of the integral from 3 to 5 of 6xy squared plus 12x squared y plus 4y dx dy. So we're going to see two integrals and a dx dy at the end. The dx dy is going to tell us the order we're going to do the integrals in. Dx is going to tell us this first integral, working from the inside out, we're going to do with respect to x. Then we'll come back and take the answer with respect to the y. So first let's look at the inside. The integral with respect to x. Well, the integral of 6xy squared, we end up with x squared. I should highlight in yellow. We're treating the x's like our variable. So x squared divided by 2 leaves a 3, y squared, plus x squared becomes x cubed, divided by 3 is 4y, plus 4xy. And we're going to integrate this from 3 to 5, and the variable we're doing is x. So let's replace the x's with 5 and 3. We have 3 times 5 squared y squared plus 4 times 5 cubed y plus 4 times 5y, and then we subtract, changing the signs, minus 3 times 3 squared y squared minus 4 times 3 cubed y minus 4 times 3y. And so when we simplify this, we get 5 squared is 25 times 3 is 75 y squared plus 5 cubed is 125 times 4 is 500 y plus 20y minus 3 squared is 9 times 3 is 27 y squared minus 3 cubed is 27. 27 times 4 is 108 y minus 12y. Combine like terms, 75 minus 27 is 48 y squared. Then we've got 500 plus 20 y, so that's 520, minus 108 is 412, minus 12y is plus 400y. That was just the inside, though. We still need, going back to the outside, the integral from 1 to 2 dy. Now we do the outside integral. Take the integral again to finish off this problem. Well, the integral of y squared is y cubed. 48 divided by 3 is 16. Plus, the integral of y is y squared. 400 divided by 2 is 200. And we're going to integrate from 1 to 2. So we have 16 times 2 cubed plus 200 times 2 squared. And then we subtract. It's going to change the signs. Minus 16 times 1 cubed minus 200 times 1. And that's simple enough. We can probably type that into our calculator. 16 times 2 cubed plus 200 times 2 squared minus 16 minus 200 is 712. And just like the way integrals found areas under a curve, what a double integral actually does for us, it finds the volume under a three-dimensional curve. So now we've got some weird shaped cup modeled by this function, and the volume underneath it between 1 and 2 on the y-axis, 3 and 5 on the x-axis, down to the z-axis. The entire volume of this cup is 712. Now here's an interesting question. I want to take the same problem, but I'm going to switch it up a bit. The other problem, we took the integral, we did 1 to 2, and then 3 to 5. I'm going to switch them. I'm going to do the 3 to 5 second and the 1 to 2 first of the same function, 6xy squared plus 12x squared y plus 4y, but then I'm also going to switch the dy and the dx. Because now you will notice the first integral, the inside integral, is a dy, and the dy is still with the range 1 to 2. When we're done with that, then we can take dx with the limits from 3 to 5. And we're going to see how this compares. So just looking at the inside integral, and we're doing dy, so the y's are the variable this time. We end up with, if I get the right color, y cubed, 6 divided by 3 is 2x, plus y squared, 12 divided by 2 is 6x squared, plus y squared, 4 divided by 2 is 2. And we're going to integrate it from 1 to 2, and that's equal to my y's. Y is 2, and y is 1. So let's plug it in. We've got 2x times 2 cubed plus 6x squared times 2 squared plus 2 times 2 squared, and then we subtract each term, changing its signs, minus 2x times 1 cubed minus 6x squared times 1 squared minus 2 times 1 squared. And let's see, what's that going to give us? 2 cubed is 8 times 2 is 16x. Plus 2 squared is 4. 4 times 6 is 24. X squared. Plus 2 squared is 4 times 2 is 8. Minus 2x minus 6x squared minus 2. Combine like terms, we'll do the squared first. 24 minus 6 is 18x squared. So I'm going to do this in gray. 18x squared. 16x minus 2x is plus 14x. And 8 minus 2 is plus 6. That's just the inside, though. We still have to do the second integral from 3 to 5, this time dx. This is now the outside integral. So we do it again. X squared becomes x cubed. 18 divided by 3 is 6. Plus x becomes x squared. 14 divided by 2 is 7. Plus 6x. And we're going to integrate this from 3 to 5. So plugging 5 in, we got 6 times 5 cubed plus 7 times 5 squared plus 6 times 5. Then we subtract, changing the signs, minus 6 times 3 cubed minus 7 times 3 squared minus 6 times 3. Cleaning it up, 5 cubed is 125 times 6 is, I think it's 750. Yep. Plus 5 squared is 25 times 7 is 175. Plus 6 times 5 is 30. Minus 3 cubed is 27 times 6 is 150, 62. minus 3 squared is 9 times 7 is 63, minus 6 times 3 is 18. And if we do all of that, 750 plus 175 plus 30 minus 162 minus 63 minus 18, we end up with a final answer of 712. The exact same answer we found, the first time. Which makes sense, because if a double integral is the volume under a curve, it doesn't matter which direction you measure it, the volume is still the same. If we measure up, then to the side, or if we measure the side, then up, you're still talking about the same container. It doesn't hold any more or any less stuff. So the volume should be the same underneath this curve. So that's all we're doing today, is we're extending the idea of integrals to kind of what we did with partial derivatives and higher ordered partial derivatives. Working from the inside out, treating the other variable like a constant. And this concludes our business calculus videos. We'll see you in class with questions. Take a look at the homework.